Okay, so here's a quick review of our differential equations sections. Let's just get started. We've got a differential equation here, dy dx equals 2y, 3 minus x. Find the general solution to the differential equation using separation of variables. I'm just going to move the y over, keeping the left side as simple as possible, and I'm going to go ahead and distribute this 2, so we get 6 minus 2x, just to make it easy when we do integration. We don't have any extra things laying around. So we'll integrate both sides and get the natural log of the absolute value of y on the left. Excuse me. And 6x minus x squared plus c on the right. Solving for y, we get e to the 6x minus x squared plus c. We've seen this e to the blah 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 plus c before. We know that brings a constant in front. So absolute value of y equals c e to the 6x minus x squared. And then that c can also absorb the plus or minus from the opposite value, so we get y equals c e to the 6x minus x squared. So using the same differential equation, we're going to find now the particular solution, or specific solution, to the differential equation if y of 4 equals 1. So remember, this is x equals 4 and y equals 1. So plugging those numbers in, we get 1 equals c e to the 6 times 4 minus 4 squared. So that's e to the, let's see, that's 24 minus 16, so that's e to the 8th. So c equals 1 over e to the 8th, which we can also write e to the negative 8th. So y equals e to the negative 8th times e to the 6th x minus x squared. Well, we can combine those. Y equals e to the 6x minus x squared minus 8. That's not too bad. Alright, here's a problem. Has its basis in calculus, but really is a pre-cal type problem. Find, especially this first one, find the amount after 18 years of an account with an initial principal of 30,000 at 4% interest. Well, if we compound it quarterly, A equals P 1 plus R over N to the NT, where A is the amount, P is the principal, R is the annual percentage rate, N is the number of times per year, and T is the number of years. So the amount is just 30,000 times 1 plus 0.04 quarterly, so divided by 4, and then 4 times 18. Type that into our calculator, and we get a quick little answer of $61,412.98. Now, if it's compounded continuously, obviously it's going to be a little bit bigger, but that's an easier formula. A equals PE to the RT, where again, principal, annual percentage rate, and the number of years. So A equals 30,000 e to the 0.04 times 18. Using our calculator again, we get 61,000, so not too much more. 633 after all the rounding dollars. So not much difference, but continuously is more, as expected. Moving on, we get to this problem here. Assume that the atmospheric pressure Y at a height, sorry about that, I had to clear my throat. Assume the atmospheric pressure Y at height x meters above sea level satisfies the relation dy over dx equals, and this should be ky. if one day at a certain location the atmospheric pressures are 760 and 675 unit for pressure at the sea level and at 1,000 meters above sea level, respectively. So at sea level, it's 760. At 1,000 meters, it's 675. Find the value of the atmospheric pressure at 600 meters above sea level. Okay, so the whole purpose of this problem, dy dx equals ky, is to see this law of exponential change here. As soon as we see that y is changing with respect to anything is proportional to y itself, we know that we can jump straight to y equals y naught e to the k, and then this variable right here, x. Just because it's a pattern that shows up all the time, so we know that. That's the law of exponential change. Then we do have two unknowns, y naught and k. That's why we had two givens here. So let's see, 760 equals y naught e to the k times sea level is 0 meters above sea level. So that's 760 equals y naught e to the 0. Anything to the 0 power is 1. So y naught is 760, which makes sense. That's our initial point. Next one, 675 equals 760, because we know that now. E to the k times 1,000 meters above sea level. We'll divide, we get 0.888. That's kind of cool. E to the 1,000 k. Take the natural log of both sides. Equals 1,000 k. Divide by 1,000, we get k equals, that'll be a negative, and then 0.000119 for k. So now we've got our two variables. Now we can use it to estimate the pressure at 600 meters. So y, the pressure, equals 760 e to the negative 0.000119 times 600. And that comes out to be 707.628. All right. So we know that the calculus was all in this, but we studied that. Here we go. Particle starts at 3 when t is 1, so not 0, but 1. It moves along the x-axis with velocity blah for t is greater than 0. Where is the particle at when t equals 4? Okay, so we have an initial starting point at t equals 1 at 3. So we're going to be at 3, and we're going to add. We were at 1, we're going to go to 1 second, we're going to go to 4 seconds, assuming we're in seconds, v of t dt. So integrating velocity will give us our distance. So let's substitute that in here, 0.5t dt. We're just going to integrate that. So we have 3 plus 3.75, which is 6.75. All right. Did they give us units? No. The rate at which customers are arrived at a counter to be served is modeled by the function f. So this. So 12 plus or minus something. Cosine is going to go back and forth between negative 1 and 1. So anywhere from 6 to 18 customers for 0 to 60. So for the next hour. Where f is measured in customers per minute and t is measured in minutes. To the nearest whole number, how many customers arrive at the counter over the 60-minute period? Well, assuming we start with 0, we're going to do a net change from 0 to 60 of f of t dt. Using our calculator, we see that comes out to be about 725 people. So remember on this one, it said to the nearest whole number, so we're not going to add the minimum 3 decimal places after the decimal. moving on to our last topic, it's slope fields. On the axis provided, sketch the slope field for dy dx equals negative. Make sure you see that negative sign. 2x over y at the points indicated. So I did a smaller set just for you to show me that you know what's going on. Remember that 0 over 0, so when x equals 0 and y equals 0, that's indeterminate, so there's not a slope there. We would have a 0 slope when x is 0 otherwise, so these are 0. We'd have a perpendicular slope or a vertical slope when y is 0, so this is vertical like this. Yeah, I just totally messed that up, didn't I? Let's try that again. We'll use orange. When x is 0, it's horizontal. X is 0 here, here, and here. And it's vertical when y is 0 here and here. Goodness. 1, 1, it's going to be a slope of -2, so it's going to look like that. 1, 2 would be a slope of -4, so it gets steeper. So start playing around, not playing around, but we start plugging in all the numbers, we can see that we're going to have slopes of 2 and -2 around here, and then 4 and -4 around here, and we're going to get this oval looking shape, right? So this is probably going to be some kind of ellipse. If we integrated that, we'd get an ellipse equation. But you don't have to know that. That's just what happens there. Sorry about that mess up there. Slope field, dy dx equals 2y minus 4x is given below. Sketch the possible solution curves through the points 0, 1 and 0, -1. Well, 0, 1 is here, and our solution set through there looks like the degenerate case. It looks like it's just a straight line, which is obviously not what it normally does. Okay, 0, -1, we get a little bit better picture of some kind of crazy looking curve down here. Make sure you don't curve back and become not a function. So following that, it looks something like that. So those are two different possible solutions. This one doesn't look like a great solution. This one looks more like we should normally find. Get some kind of different, if we'd chosen something over here, it looks something like that. So kind of different areas, you get something slightly different. But that's your slope fields.